Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 3450, Mission to Mars, Lecture 8, the Space Shuttle program. In our last lecture, we saw the Apollo program, the missions to the moon, from the very beginning up until Apollo 17 in December of 1972. But a few years before Apollo 17, it was realized that the Apollo program was coming to an end, and that the United States and NASA would need something to continue beyond Apollo. In January of 1969, keeping in mind that this is before the Apollo program had even achieved its objective of landing a person on the moon and returning them safely to Earth, which didn't happen until July of 1969. But in January of 69, President Richard Nixon formed a space task group to study what would come after Apollo. Now, this was a different space task group than the one we've talked about before. This particular space task group was chaired by Vice President Spiro Agnew, and they recommended three things to the President of the United States. They recommended a large, permanently crewed space station in Earth orbit. They recommended a reusable spaceplane that could be used to build and resupply the space station. And they recommended a human mission to Mars. The problem is that all three of these combined would require a significant increase in NASA's budget. And with the costs of the Vietnam War, President Nixon felt that that was not realistic and asked Vice President Agnew to pick one of the three. After studying the problem, Agnew picked the reusable space plane. And so in January of 1972, President Nixon stated, "I have decided today that the United States should proceed at once with the development of an entirely new type of space transportation system designed to help transform the space frontier of the 1970s into familiar territory, easily accessible for human endeavor in the 1980s and the 1990s. This went on to be known as the Space Transportation System, STS, or colloquially known as the Space Shuttle program. And the goal here was to make access to space easy, routine, and inexpensive. With the Apollo missions, it was difficult and expensive to get to space. This was designed to be a reusable space truck, as it was sometimes called, that could get human astronauts and cargo into orbit quite often and very inexpensively. Now, in order to do that, it would probably have to largely be reusable. You'll remember that the Saturn V was completely disposable. There were no reusable parts on the Saturn V. The first and second stages ended up in the ocean. The third stage ended up in orbit around the sun. The lunar module was discarded on the moon. And even the Apollo command and service modules, when they came back to Earth, the service module burned up in the atmosphere and only the command module came home. But even it was not reusable. The Saturn V rocket was completely disposable. To bring down costs, they'd need a reusable transportation system. And that reuse would hopefully significantly reduce the cost of getting to orbit. They wanted to bring the cost getting to orbit significantly down so that we could launch more often and launch larger payloads. The goal here was to launch about 50 times per year, about once per week. And such a system could not only serve NASA, but it could also serve as the primary launch vehicle for the U.S. Department of Defense. Lots of ideas were put forth for the Space Shuttle. You can see a couple pictures of them here. We'll talk about the final selection in a minute, what the final system looked like. There was even a Space Shuttle mounted on the side of a Saturn V rocket as one of the early plans for the space transportation system. But the final space transportation system, the final space shuttle system, consisted of three things. It consisted of a winged reusable orbiter, an expendable external tank, and two solid rocket reusable boosters. And so this is what the space shuttle looks like, the final space shuttle system. Again, the three parts are the winged orbiter itself, the giant external tank, and then the two solid rocket boosters. And we'll go over all of these in detail. I just wanted to show you this particular picture. It's one of my favorite pictures of the space shuttle. This is taken right before STS-79. That is the Space Shuttle Atlantis mounted to the external tank and with the two solid rocket boosters there on the side. And it shows you what the Space Shuttle system looked like from a nose-on perspective. Now, ultimately, the United States built one test vehicle. That was the Enterprise, and the Enterprise was only used in tests on Earth, never flew in space. They used to put it on the back of a an old converted Boeing 747 airliner, fly it up to altitudes, and then they would drop the Enterprise off the back of the 747 and let it glide down to Earth to test the aerodynamic properties and the flight properties of the Space Shuttle. But Enterprise, just to emphasize, never flew in space. 5 orbiters were eventually built: Columbia, Challenger, Discovery, Atlantis, and Endeavour. 2 of them, Columbia and Challenger, would tragically be lost in accidents that also meant the loss of their crews. Endeavour was a late replacement, and it was designed to replace the Space Shuttle Challenger after it was destroyed in 1986. The Space Shuttle was quite respectable in terms of the payload that it could bring to orbit. In fact, it was quite significant for its day. It was able to bring 24,310 kilograms to low Earth orbit. For comparison, today, the Falcon 9 rocket can bring about 22,800 kilograms to low Earth orbit, and the Delta IV Heavy rocket can bring about 28,000 kilograms to low Earth orbit. So the Space Shuttle was comparable to the modern launch vehicles, the larger of the modern launch vehicles that we have today, and it could lift significantly more mass to low Earth orbit than the smaller vehicles, the smaller rockets like the Atlas V or the Delta II. The Atlas or the Delta II. The Space Shuttle orbiter itself consisted of 4 parts. There was a crew cabin, a payload bay, an engine compartment, and then the wings and the thermal protection system. So let me just start by showing you a couple of really cool pictures of the Space Shuttle in orbit around the Earth. This is a picture of the Space Shuttle Discovery on STS-121 with the Earth in the background. This picture was taken from the International Space Station as Discovery was approaching the space station. A couple cool things you can see here is it's a beautiful view of the remote manipulator system, the robotic arm inside the Space Shuttle bay that could be used to lift material out of the Space Shuttle bay, out of the cargo bay, the payload bay, to work on it. You can see the 2 cargo doors on the payload bay are open. The crew compartment is up front right here. The payload bay is in the middle of the Space Shuttle. The engine compartment is at the tail, and then of course the wings with the thermal protection system underneath. Here's another view. This is of STS-132 Atlantis. Again, another picture taken from the International Space Station just after Atlantis had completed a mission to deliver a module to the International Space Station. So this shows very nicely the main parts. The crew cabin up front, the front part of the Space Shuttle, the payload bay in the middle, the engines down here at the bottom, and then the wings and the thermal protection system. Ultimately, I think the Space Shuttle will go down in history as one of the most amazing flying machines that humans have ever invented. It really is a remarkable piece of technology and a remarkable piece of engineering. But we'll have to wait till the end of the lecture to find out whether it ever met its goals of getting things to space routinely and inexpensively. For now, let's look at the orbiter itself. Those main 4 parts again are the crew cabin, the payload bay, the engine compartment, and the wings and the thermal protection system. The crew would live and work and launch inside of the crew cabin. And it's important to realize that the crew cabin is the only place that astronauts could access without a spacesuit. That is, there were no other places that they could access inside the shuttle orbiter. Now, the crew cabin here at the front consisted of a flight deck or upper deck and a middle deck or mid deck. There was also a lower deck, but the lower deck was not accessed during flight. The crew would spend all of their time on the flight deck or the mid deck. Now, for an agency that had been used to flying capsules, which were typically the inside of the Apollo capsule, for example, had about the inside volume of a minivan, the Space Shuttle seemed quite spacious. That said, as you look at these pictures, you'll realize it was a lot tinier and a lot more cramped than you might imagine. So if we look at the flight deck, for example, here is an image of what the flight deck of the Space Shuttle looked like towards the end of its lifetime. Early on in the Space Shuttle program, the instruments inside the Space Shuttle consisted of old-fashioned CRT terminals and some actual flight instruments that they weren't the modern digital flight instruments that we have today. And over time, all of these avionics on the Space Shuttle were replaced with modern replacements. You can see a heads-up display, for example, that was used in landing the Space Shuttle. You can see the digital displays here. So this is what the interior, the forward-looking interior of the upper deck of the Space Shuttle looked like, the flight deck looked like towards the end of the Space Shuttle program. To give you an idea of how big the flight deck was, this is looking from the commander's seat towards the back of the flight deck. And now suddenly you realize that there's not a lot of room there. You can realize that there's especially not a lot of room when on launch, not only would the commander be in their seat and the pilot be in their seat, but there would be two mission specialists that sat behind them in two seats that would be disassembled and stowed away on orbit, but during launch would be located here and here. So you realize that that flight deck, that upper deck, was fairly cramped. Back here, you can see the windows that look out over the payload bay, the joystick that was used to control the remote manipulator system, the robotic arm that was out there, and then lots of functions, lots of displays and control over the equipment in the payload bay. The mid-deck down below was where four crew members would be located for launch. Now, the mid-deck had no view outside except through a small window here. And other than that window, they didn't have a view outside. But the mid-deck looks quite spacious right here, but this is not what it would look like in flight. During a flight, the mid-deck, which again had 4 chairs at launch, which would, after launch, would be packed up and stowed away so that they would be out of the way, you would see that during launch, the mid-deck down there was filled with bags, filled with cargo, strapped to the walls, strapped to the ceiling. Equipment would be mounted in the mid-deck. The mid-deck was typically where the astronauts would sleep while they were on orbit. One of the nice things about sleeping in weightlessness is because you're weightless, you don't need to sleep on anything. But to keep you from floating away, you would typically sleep in a lightweight sleeping bag, and then you would strap yourself to the wall just to keep yourself from floating off. Some people like that feeling of being pressed into a bed so they could put bands over their heads. Others would just free float. But this is what it looked like when the crew was sleeping down there on the middeck. You can see one of the chairs here that was used for launch. So you can see even with the spaciousness of the space shuttle compared to the previous capsules, it was really quite tiny. Let's talk about the payload bay. The payload bay was unpressurized. That is, it's exposed to the vacuum of space. But the payload bay was enormous by standards of the day when the space shuttle first launched. It could carry huge cargo up to the International Space Station. For example, this is one of the logistics modules that the Italian Space Agency built that would be used to bring cargo up to the International Space Station. At the front of the space shuttle here in the cargo bay, you see an airlock mounted. In order for astronauts to go on a spacewalk, there was no airlock in the space shuttle itself. They had to mount and bring with them a separate airlock that would be mounted in the space shuttle cargo bay and then accessed into the middeck through a hatch down there. So that is the airlock there, and then other logistics modules in here. The payload bay could be configured in many different ways. Again, for example, we see here, this is a space hab. This is a little facility where the astronauts can crawl through a tunnel and then do work and experiments in here. Again, we see the airlock right there that would be used for going on a spacewalk. We see other things stored in the cargo bay. The cargo bay had the ability to carry enormous cargo into orbit, enormous and very heavy cargo into orbit. Of course, two of the most impressive satellites that were launched were the Hubble Space Telescope on STS-61. So you can see the Hubble Space Telescope being serviced here, sitting on a rotating platform there, being serviced by the astronauts. It was used to launch spacecraft into space, the Magellan spacecraft, for example, which went on to Venus. It was used in a rescue of a commercial communications satellite that was stranded in low Earth orbit when its booster failed to fire properly. And then the heaviest cargo that the space shuttle ever launched was the Chandra X-ray Observatory for astronomers, weighing 22,753 kilograms. You can see it filling the space shuttle cargo bay right there, literally going from the front to the back of the space shuttle cargo bay. You can see the two little windows there that lead from the flight deck to the payload bay. And then here's a picture of the space shuttle carrying the Destiny module, one of the science modules that was mounted on the International Space Station. At the rear of the orbiter is the engine compartment back here, and the engine compartment housed the three giant RS-25 engines. The RS-25 is a liquid hydrogen, liquid oxygen fueled engine that were developed specifically for the space shuttle, and they were specifically designed to be reusable. In addition, the engine compartment contained the orbital maneuvering system, these two large thrusters right here that were used to bring the space shuttle out of orbit. They could also be used for changing the orbit of the space shuttle, and then it consisted of a couple smaller thrusters that could be used for orienting the spacecraft or doing very small maneuvers in orbit. Now, the RS-25, as I mentioned, is fueled by liquid hydrogen and liquid oxygen. And if you take hydrogen and oxygen and mix them and ignite them, they burn and they form water vapor. So the three RS-25 engines produced an extremely clean exhaust. The only thing coming out of the exhaust of the RS-25 engine was water vapor. And you can see in this image here that it was almost completely transparent. Where the exhaust comes together right there, you can see three cones called Mach cones, where the exhaust comes out and forms those three cones. And you can certainly compare it to the exhaust coming out of the solid rocket boosters, which was white in color and glowed because of the tiny particulates that came out of it. We'll talk about that in a minute. So that's the RS-25 engine. And there it is, the RS-25 up close. The top half was called the power head on the engine. This contained the two giant pumps, the fuel pump and the oxidizer pump that would pump the hydrogen, liquid hydrogen fuel and the liquid oxygen into the engine at very high speed. But then there were all kinds of other mechanisms on the pump. Those pumps themselves were fueled by liquid hydrogen and liquid oxygen. So there was piping to get them up and going, and then all kinds of other monitoring and control systems. The RS-25 was built by Aerojet Rocketdyne, and they were designed from the very beginning to be reusable. Each one of these engines produces about 1,859,000 newtons of thrust. That's about 418,000 pounds of thrust, and they could burn for 8.5 minutes. The goal of these engines was that after the mission, of course, they would return because they would remain attached to the space shuttle. And once they were brought back, they could be pulled out of the orbiter. And the goal was that they would not require much maintenance. They could be refurbished and they could be used again on a future shuttle mission. Altogether, 46 RS-25 engines were built during the space shuttle program at a cost of about $40 million per engine. And to put that in perspective, a single RS-25 engine for the space shuttle cost more than the whole first stage for a Falcon 9 rocket. The engine itself was quite complex. To give you an idea of the complexity of this thing, this is the high pressure fuel turbo pump right here. So this is what would pump the high pressure hydrogen fuel into the combustion chamber. There was another turbo pump over here that was pumping oxygen into the combustion chamber. This high pressure pump over here that was pumping the fuel into the chamber, that would spin at 35,360 revolutions per minute. Think about that, 35,000 revolutions per minute. That's more than 500 revolutions per second. And it would produce a total power of about 53 million watts or 71,000 horsepower. That's how powerful this pump alone was. The oxygen pump was not quite as powerful, but it would pump oxygen into the combustion chamber. This was pumping fuel into the combustion chamber. The hydrogen and oxygen were lit inside that chamber. They would combust inside the combustion chamber, pass through this very narrow throat right here, out into the nozzle where they would expand, pushing against the nozzle, pushing the shuttle forward as they were exhausted out the back of the rocket. And then if you're interested, you can look at this picture to see what all these other lines are for. But basically the turbo pumps themselves were powered by fuel and oxygen, because they had little miniature turbines in there, and they would use the hydrogen and the oxygen would be burned inside these turbines to spin those pumps that rapidly. The next part of the space shuttle system were the wings and the thermal protection system. Now the wings, the space shuttle was what's termed a delta wing. It had the funny quote about the space shuttle is it had the flying properties of a brick. Remember, the space shuttle was a glider more than it was an aircraft. As the space shuttle would enter the atmosphere and come down, it no longer had any engines. The main engines, these RS-25 engines, got all of their fuel from that giant orange external tank. Once that external tank was discarded early in the mission, these engines no longer had any fuel. And so the space shuttle, as it was coming down, gliding to a landing, had no ability to power up its engines and go around for a second chance. So they had to always land it on the first try. That, on top of the fact that the space shuttle did not fly very well intentionally because it was a giant glider, meant that it was what you would term a really high-performance aircraft. So it took really skilled pilots to bring the space shuttle down. And remarkably, in the 135 flights of the space shuttle program, other than Columbia burning up on reentry, the space shuttle landings all went remarkably well. The wings, though, also contained the thermal protection system. This was the system that was designed to protect the space shuttle on re-entry through the Earth's atmosphere. The space shuttle would come in with the bottom exposed to the atmosphere as it would move through, and so the bottom would get very hot. The bottom itself consisted of high-temperature reusable surface insulation. We'll talk about the tiles here in a second. There was also let's talk about the different parts of the heat protection system. So the first thing is the high temperature reusable surface insulation. These were tiles that were mounted on the bottom of the space shuttle. If you look at the bottom of the space shuttle, you will see that the bottom of the space shuttle was covered in thousands upon thousands of these ceramic tiles. These ceramic tiles were this high-temperature reusable surface insulation. There were 20,458 of them on the bottom of each orbiter. And they were in the area of the fuselage, down in the forward fuselage, part of the orbital maneuvering system up at the top, the vertical stabilizer. They're made of pure silica fibers. They're very low density, very lightweight, and they could withstand temperatures up to about 2,900 degrees Fahrenheit, about 1,600 Celsius. So those were the heat tiles on the bottom of the space shuttle. Now, parts of the space shuttle would get exceptionally hot on re-entry, and those places that would get exceptionally hot were the tip of the nose right here and the leading edge of the wings right there. And because they would get so hot, they would get hot enough that the silica tiles could not withstand those temperatures, and they used something else called reinforced carbon-carbon panels. And these could withstand temperatures up to 2,750 degrees Fahrenheit, or about 1,500 Celsius. So that was what was used on the nose and the leading edge of the wing right here. There's a picture of the reinforced carbon-carbon panel on the nose of the shuttle, and then, of course, the reinforced carbon-carbon panels on the wing. With the loss of the space shuttle Columbia, the Columbia was lost because a piece of debris broke off of the external tank during launch, and it actually struck one of the reinforced carbon-carbon panels on the leading edge of the left wing of Columbia, actually breaking that panel, putting a huge hole in that panel that was not realized during launch and while the astronauts were in orbit. And then on reentry, hot gases were able to enter the wing through that hole, and they melted the interior structure of the wing, and that caused the loss of the space shuttle Columbia. I mentioned earlier that some of those heat protecting tiles were used here where it would get hot between the windshield up on the leading edge of the tail right there, and you can see some tiles on the leading edge of the orbital maneuvering system pods there at the back. So you can see some of those tiles there as well. Most of the rest of the Space Shuttle orbiter was covered in these insulation blankets. They did not have to withstand very high temperatures on reentry, and so the rest of the shuttle orbiter was covered with those blanket materials. The external tank would carry the liquid hydrogen and liquid oxygen as the Space Shuttle went to orbit. So here's a picture of what the giant external tank looked like. There it is in the vehicle assembly building. These two attachment points here, these are the aft attachment points where the shuttle would be attached, and then the nose of the shuttle would be attached up here at the front. These external tanks were manufactured at the NASA McCoud Assembly Facility in Louisiana, and they would be shipped to the Kennedy Space Center on a giant barge. So that's how they got to the Kennedy Space Center. They consisted of a giant liquid hydrogen tank right here. So this tank contained the liquid hydrogen, and the nose contained a giant liquid oxygen tank. And that giant, those giant tanks, the liquid oxygen tank would feed out through a tube on the outside of the external tank. The hydrogen would feed through a tube on the inside of the tank, and they would come up here to these two supply lines that were actually mated to the bottom of the shuttle orbiter. So the fuel would flow out, the fuel and the oxidizer would flow down these lines, and they would flow out and into the space shuttle through those lines. This is a picture of the size of the external tank. Because liquid hydrogen and liquid oxygen are both at cryogenic temperatures, which means they're both hundreds of degrees below zero, they're very, very cold, this external tank was covered in this orange insulating foam. That orange insulating foam was to keep ice from forming on the outside of the external tank. If they didn't have that foam there, significant amounts of ice would form on the exterior of that tank. Now, you might remember from the Saturn V launch and even rocket launches today, on many of the space vehicles, you can see that coating of ice on the outside of the rocket. And that's fine because as the rocket launches, that ice just sheds off, it falls to the ground. They couldn't allow that to happen on the space shuttle, though, because, of course, any ice that would break off of the external tank would have the possibility of coming down and striking the orbiter itself. And in fact, as I said, tragically, a piece of foam from right under the nose here, where the nose of the space shuttle connects to the external tank, it was a piece of foam that broke off that struck Columbia on its front left wing, causing the Columbia accident. But ice could be shed off this tank, so to prevent that, it was coated in this orange insulating foam. And later in the space shuttle program, they had lots of trouble with this foam actually shedding off the tank. Little pieces would occasionally break off and hit the shuttle orbiter. And interestingly, I fell into a trap there. I shouldn't say it was late in the shuttle program. In fact, that was happening throughout the whole shuttle program. It wasn't until the Columbia accident that NASA realized how dangerous it was that that foam was coming off the external tank and hitting the orbiter. There's a picture of the inside of the external tank. Now, what's interesting about the external tank is the external tank made it to orbit, or could have made it to orbit. Because it was powering the main engines on the space shuttle had to bring this tank all the way up to orbit with it. Typically, what was done was the tank was just ejected from the shuttle. It was just discarded. It was placed on a trajectory that would bring it back down, and it would typically re-enter over the Indian Ocean or out over the South Pacific Ocean and just burn up on re-entry. Lots of plans had been hatched over the decades that the shuttle flew to find some use for these external tanks. If we could just keep them in orbit, maybe we could turn them into a space station or something else. But nothing ever came of that, and they were all discarded and burned up in the atmosphere. The last part of the shuttle the shuttle stack, as it's called, are the solid rocket boosters. And each space shuttle flew with two giant solid rocket boosters. They were manufactured by Thiokol in Brigham City, Utah. They were the most powerful solid rocket motors that were ever flown. Each one provided 3.3 million pounds of thrust, and the two of them combined were 71% of the thrust at liftoff. So those solid rocket boosters were providing most of the thrust at liftoff. They were also most of the mass at liftoff, about almost 70% of the mass of the space shuttle stack at liftoff. Now, the boosters themselves only burned for a little bit more than 2 minutes, over 127 seconds. And when the space shuttle was about 45 kilometers in altitude, about 28 miles, traveling about 5,000 kilometers an hour, the two solid rocket boosters would detach from the external tank and they would come back to Earth. Now, you might wonder, what do I mean by solid rocket boosters? What I mean by solid rocket boosters is the fuel inside of them was not liquid. It was a solid fuel. And it was made up of aluminum powder. That's just plain old powdered aluminum. It was mixed with, that was the fuel. It was mixed with an oxidizer, ammonium perchlorate. It was mixed with a catalyst, iron oxide, which is just slightly rusted iron. Binder and fuel. There was a binder that was used to bind this all together, to hold it all together. You could think of it like a glue. And then there was a little bit of epoxy curing agent in there. So that was the fuel that was inside the solid rocket boosters. This is what the solid rocket boosters look like when they are mounted on the giant mobile launch platform. When they were stacking the space shuttle, they would start by stacking the two solid rocket boosters on the mobile launch platform. As we'll see later, the mobile launch platform was what was used to take the space shuttle out to the launch pad, and they would start by stacking the boosters there. Now, the boosters themselves consisted of 4 individual segments. The boosters were too big to ship from Utah, so they were shipped by train in individual containers right here, with boxcars in between to shield them in case there should be an accident. These boxcars would provide a little bit of cushioning so that the solid rocket boosters wouldn't explode, because they're fully loaded with fuel at this point when they're being shipped from Ohio. So they're quite dangerous should they get into an accident. Once they arrived at the Kennedy Space Center, they were unloaded from their cars. So here's the container that they were in. That's the solid rocket booster itself. They were lifted off the train car. They were brought into the vehicle assembly building, and then they were stacked one on top of the other. And there you can see the fuel inside the solid rocket booster. It had a very rubbery-like texture. It wasn't a hard solid. It was very rubbery, but that was the fuel used in the solid rocket boosters. After the solid rocket boosters burned out, those empty boosters, they burn all the fuel, right? All this fuel would eventually burn out of the inside of the booster, so all that were left were the casings. Those empty casings would parachute back down to the ocean. As they dropped into the ocean, air would be trapped in the top of the booster, so they would float upright like this, and NASA would send a ship out, and that ship would retrieve the boosters, tow them back to port. They would be cleaned up, and they would be reused over and over again. At the Kennedy Space Center, the shuttle itself was processed in a facility called the Orbiter Processing Facility. There were 4 of these at the Kennedy Space Center, one for each of the space shuttles that was flying at the time. Inside the Orbiter Processing Facility was a huge system for maintaining the space shuttle. This is a picture of the inside of the Orbiter Processing Facility, and it's called the High Bay inside the Orbiter Processing Facility. And believe it or not, inside the middle of all of that is the Space Shuttle Atlantis. If you look very, very hard, you can see the nose of the Space Shuttle Atlantis, the reinforced carbon-carbon panel on the tip of the nose of the Atlantis there. But Atlantis is encased inside of all of this scaffolding and all of this equipment. This would allow technicians access to every inch of the space shuttle. Inside that scaffolding, there was a clean room where they could open the cargo bay doors of the space shuttle and they could access anything in the cargo bay. They could load the cargo bay here, for example, if desired. They could access equipment and panels underneath the cargo bay. They had access to the thermal tiles from underneath. They had access to every part of the space shuttle here in the Orbiter Processing Facility. When an orbiter was ready to fly, it would be transported over to the giant vehicle assembly building. You'll remember this was the giant building that was built in the 1960s to stack the Saturn V rocket. The Space Shuttle orbiter would be brought over on a giant trailer, and then once it was in the vehicle assembly building, it would be hooked up to a lifting fixture. That lifting fixture would lift the shuttle off the trailer, would turn the space shuttle upright so that it is vertical, would then lift the space shuttle high into the vehicle assembly building and made it to the stack of the external tank and the solid rocket boosters. I think this picture here just gives you a great view of the vast size of the interior of the vehicle assembly building, where we've got the external tank, the 2 solid rocket boosters, and the space shuttle just suspended way above them with plenty of room to spare inside this giant vehicle assembly building. And of course, once it was stacked up, then it was ready to be transported to the launch pad. It was transported to the launch pad on the mobile launch transporter. So this is the mobile transporter right here. This dates back to the days of the Apollo missions to the moon. It's basically a launch platform right here, and then underneath it is the machinery, the large treaded machinery that's used to drive it very slowly across the ground and take it out to the launch pad. At this time, the external tank, of course, is empty. The only thing that has the fuel in it are the solid rocket boosters. Once the space shuttle comes out to the launch pad, it travels up a steep ramp here that brings it up to the launch pad. The mobile launch platform right here has the ability to tilt, so the shuttle is always kept perfectly level. It has hydraulics in there that can tip it back and forth so that even as it goes up this incline, the space shuttle is kept vertical right there. The space shuttle climbs up this incline to the launch tower. Once it's at the launch tower, so here it is on the mobile launch platform, this giant structure right here was called the rotating service structure. And the rotating service structure would rotate around and it would enclose the space shuttle. And that would allow them to open the cargo bay doors on the space shuttle so that they could continue to access things inside the cargo bay and continue to work on the space shuttle. Right before launch, typically the night before launch, that rotating service structure would be rotated out of the way so that it would be clear during launch. So I thought I would show you one video of the launch of the space shuttle. I've got a couple more here. You're welcome to watch them if you get the chance. There are lots and lots of great high-def videos of the launch of the space shuttle. Well worth watching because, again, this is probably the most spectacular flying machine that humans ever made.
All systems are go. We're about 90 seconds from the launch of Space Shuttle Discovery. T-minus 60 seconds and counting. We are transferring to orbiter internal power at this time. Discovery is now running off its 3 onboard fuel cells. Coming up on a go for auto sequence start. And we have a go for auto sequence start. Discovery's onboard computers have primary control of all the vehicle's critical functions. T-minus 17 seconds and counting. 15, 12, 11, 10, 9, 8, 7, 6, start, 2, 1, booster ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond. Throttle up, crawling down by Commander Steve Lindsay. Solid rocket booster separation confirmed. Guidance now converging. Discovery's onboard computers commanding the main engine nozzles to swivel, aiming the shuttle for its precise target in space for main engine cutoff.
Okay, you sound good.
There are lots more spectacular videos of the space shuttle launching and landing that you can find on the internet.
Discovery Houston, negative return.
And I highly recommend that you search out some of them just because, again, it was such a spectacular vehicle. Well, once the Space Shuttle orbiter got to orbit, it would discard that external tank, which would typically burn up on that first orbit as it would come down over the Indian Ocean or over the South Pacific. The Space Shuttle would stay in orbit as much as more than 2 weeks in orbit. And then when it was time to come down, the Space Shuttle would enter through the Earth's atmosphere using that thermal protection system on the bottom of the shuttle to use the drag from the Earth's atmosphere to slow itself down, but that drag would create a tremendous amount of heat, and that heat was would the thermal protection system would protect the Space Shuttle from that heat. Depending on the particular mission, a typical deorbit burn, for example, if they were landing here at the Kennedy Space Center in Florida, a typical deorbit burn would take place just west of Australia over the southern Indian Ocean. Usually the shuttle flew upside down and backwards as it was orbiting the Earth. They would fire the OMS engines, that orbital maneuvering system, to slow themselves down. They would then flip the space shuttle over so that the bottom was exposed to the atmosphere, so the bottom was in the direction that they were traveling. And again, they would use that drag with the Earth's atmosphere to slow themselves down. This is a picture of STS-135 as it entered the atmosphere as photographed from the space station. And you can see that as it plows through the atmosphere, it actually is going so fast that it creates a trail of plasma behind it. That glowing plasma are atoms, molecules in the Earth's atmosphere that are excited to glow. Here's another picture of a different landing where they were coming onto the Kennedy Space Center from the northwest. So they would come in over Seattle, Washington, out over the U.S., and then land at the Kennedy Space Center. You can see the speed here is a function of the speed of sound. So Mach 1 is the speed of sound. So here over Wyoming, for example, they'd be traveling at 22 times the speed of sound, slowing down the whole way thanks to atmospheric drag. Now remember, the space shuttle didn't have an engine that they could go around, so they had exactly one and only one chance to land properly on the runway. So landing the space shuttle was all about managing the amount of energy that you had. If you had a little bit too much energy and you needed to bleed it off, you needed to get rid of it before landing. If you didn't have quite enough energy, you needed to make sure that you didn't land short. And what they would do to do that is they had a heading alignment cone. They would fly the space shuttle at the very last thing it would do as it was coming in, entering through the atmosphere. Right before it landed, it would fly on a giant circle. It would make a circle around a giant cone, and that was called the heading alignment cone. And what that would allow them to do is, if they were a little bit high on energy or a little bit low on energy, they could make the cone slightly larger or slightly smaller. This would allow them to bleed off extra energy but make up for any lost energy so that they could still land on the runway. This is what the shuttle landing facility at the Kennedy Space Center looks like. Just essentially a very long runway, about 5,000 meters, 15,000 feet long. And it was wider than your typical commercial runway. It was about 100 meters wide, about 300 feet wide. And then it had overruns on either end. Now, how was the space shuttle missions numbered? Because I've talked a couple times about STS-121 or STS-51L. How were they numbered? They were numbered sequentially. So the first flight was STS-1, the second flight was STS-2, the third flight was STS-3. And then in 1984, they changed the numbering system for a while. They changed the numbering system so that the first number would be the digit of the year in which the shuttle was launched. So for example, the 4 would be 1984. 1 was to indicate where the shuttle was launched from. Now, in the end, the space shuttle was only ever launched from Cape Canaveral, from the Kennedy Space Center in Florida. Initially, though, it was called for the space shuttle being launched out of a launch pad that was being built at Vandenberg Air Force Base in California, so that the space shuttle could undertake polar missions, polar orbiting missions. But after the Space Shuttle Challenger accident in 1986, they abandoned plans to ever launch it out of California. So it was originally designed so that the 4 would be the year they were launching in, the 1 would be where they launched from, and then the letter would indicate the sequence for that year. So A would be the first launch, B would be the second launch, and on and on. After the Challenger accident in January of 1986, they simply returned back to the old numbering system of numbering them sequentially. So the first flight after Challenger was STS-26. Now, there were a total of 135 space shuttle missions. I'm only going to go through a couple really important ones here. The first one, STS-1, was launched on April the 12th, 1981. You should recognize April the 12th as being an important day in spaceflight history. Of course, that is the anniversary of Yuri Gagarin's flight into orbit. The commander on this first mission was John Young. You'll remember John Young flew 2 Gemini missions, commanded the Apollo 16 mission to the moon, and commanded the first flight of the space shuttle. And his pilot was Robert Crippen. And he was a rookie. This was his first flight into space. STS-7 was the flight of the Challenger, and was a flight of the Challenger, Space Shuttle Challenger, June of 1983, and that is noticeable because that was the first flight of a U.S. woman astronaut, Sally Ride. So Sally Ride was the first U.S. woman in space. They deployed 2 communications satellites. STS-8 in between August and September of 1983 flew on the Space Shuttle Challenger, and that's significant because Guy Bluford flew on that mission, and he was the first African-American astronaut to fly in space. That was also the first night launch of the Space Shuttle program. Then in January of 1986, of course, there was the Space Shuttle Challenger disaster. The Space Shuttle Challenger exploded 73 seconds after launch. It turns out that the night before was an exceptionally cold night. Those 2 giant solid rocket boosters, on one of them, the joint where one booster met the other booster, there were rubber O-rings in there, and because of the cold, those rubber O-rings had shrank. They didn't do a good job of sealing the joint between the 2 boosters. At launch, when that solid rocket booster was ignited, hot gas got around that joint, started eroding that rubber gasket, started eroding the joint. It allowed hot flame eventually to escape out the side of that solid rocket booster and impinge on the one of the struts that was holding the space shuttle to the external tank, and eventually it burned through that strut and caused the destruction of the space shuttle, with the loss of all 7 crew members, including Krista McAuliffe, who was the first civilian teacher in space. So she was a teacher who had left her teaching job to become a NASA astronaut, specifically to be an educator in space. And unfortunately, she was tragically killed in that accident. Another accident was the STS-107 flight of Columbia, January to February of 2003. A very successful SpaceHab flight, a microgravity mission where they were doing experiments with the small amount of gravity that they have on the space shuttle. This was the one where a piece of foam broke off the external tank right down here, where the nose of the space shuttle meets the external tank right there, where that nose is held on. A piece of foam broke off from there, struck the left wing of the orbiter, punctured a hole through the reinforced carbon-carbon panels on the front wing, and then during re-entry, that allowed hot gases to get in. Those hot gases melted and eroded the structure inside the wing. This wing eventually failed, and then the space shuttle disintegrated and burned up on re-entry, again causing a loss of all 7 crew members. So here's the Space Shuttle program by the numbers. There were 135 flights of the Space Shuttle over 31 years. The Space Shuttle was retired in 2011. That comes out to about 4 flights per year. And you might remember that the original goal was about almost 50. It was 48 flights per year, and it actually averaged about 4 flights per year. Total cost of the Space Shuttle program was about $209 billion, which means divide that by the 135 flights, and you come out with a cost of about $1.5 billion per flight. The original goal had been about $50 million per flight. And this meant that the Space Shuttle was, in fact, remember that its goal was to get things to space inexpensively. I would argue that in hindsight, the Space Shuttle probably was the most expensive launch system that humans ever devised. It in fact, did not only not meet its goal, it was the exact opposite of its goal. It was an incredibly expensive way to get things to orbit. Altogether, though, it did lift a tremendous amount of cargo to space. It brought up about 1.6 million kilograms, about 3.5 million pounds of cargo lifted to orbit. That's more than half of all the cargo that's been launched to space since the very first space flight in 1957. There were 8,280 days of human spaceflight, 21,030 orbits of the Earth. A total of 833 crew members flew on the Space Shuttle. Now, that includes people who flew 2 or 3 or 4 or 5 or 6 or 7 times on the Space Shuttle. Of those 833, 355 were unique crew members. That is, 355 individual people flew on the Space Shuttle, 306 men and 49 women. It deployed a total of 180 satellites. There were 37 dockings with the International Space Station, 9 dockings with the Russian space station Mir. In the whole history of the Space Shuttle program, there were only 2 female shuttle commanders. One Mercury astronaut flew on the Space Shuttle, and that was John Glenn. After he retired from the U.S. Senate, flew on STS-95 in 1998, and at the age of 77 is the oldest person ever to have flown in space. And then, of course, 14 astronauts were tragically killed in 2 Space Shuttle accidents. That's all I'm going to say about the Space Shuttle program. I'm going to move on now to talk about the International Space Station in orbit around the Earth, and that'll be in Lecture 9. There's a lot to talk about with the Space Shuttle program. The Space Shuttle program was the primary U.S. space program from 1981 up until 2011. I'm not going to spend a lot of time on it because I don't know that it's very relevant to what's going to happen in the future with the mission to Mars. If we were studying the history of the space program, we'd spend a good fraction, most of the class, I would argue, on what happened with the Space Shuttle. We learned a lot of valuable lessons with the Space Shuttle. We learned how to begin to live and work in space, how to fly to space routinely. We learned a tremendous amount about training crews for space missions. There were a lot of really good things that came out of the Space Shuttle program. But ultimately, now that I can reflect on it 10 years after the Space Shuttle program ended, I have to say that it never met its goal of routinely and safely getting things into space and doing it inexpensively. It ended up being the most expensive launch system devised by humans. It also ended up being one of the most dangerous. And for those reasons, the Space Shuttle was retired. And in a few lectures from now, we will talk about the launch vehicles that are replacing the Space Shuttle. But join me in the next lecture, Lecture 9, when we talk about the International Space Station.